So just to look at where we're at. All right. And I'm going to see if I can get some webcasting so that we can get stuff up there. So under week 2, what we have now up in the Blackboard is I went in and created a PDF that is supposedly reader accessible of all my chapter 13 notes. So I'm going to kind of whiz through chapter 13 today, and we can kind of start diving a little bit into chapter 14. And it's stuff that you've seen before. It's just that we're taking it that next step. I have posted this MIT courseware. This is their graduate dynamics course, but they are referring back to the Hitler examples. So that's something that's a resource for you. I've also got some dynamics examples that came out of Cal State. I think it's Cal State. That they've done some dynamics problems and worked through some dynamics problems in what we're doing. And then I've got some additional video resources that might be helpful for you. So hopefully that will start getting that extra information. Yeah.
There's a guy on YouTube named Jim Lawrence. He's good.
There's a couple really good ones that are out there. It's just whether you're getting it from the physics side or the and again, it's not anything that we haven't already done. But I will tell you, when I started diving into chapter 14, I don't know why, and part of it is because I come from the physics side, okay? I'm not necessarily, quote, an engineer, and so I never took engineering dynamics. I took classical mechanics, analytical mechanics, physical dynamics. So my books use a little slightly different conventions and notations, but our book is going to use a notation that's going, now why the heck would you do that? But well, anyway, we'll get there. We'll figure it out. But that kind of tells you where we are in terms of the information. Now I think, and that's what I was going to go ahead and dive into over here, going to Mastering Engineering and see what we've got from due. So from due dates, I did change section 13 from it was going to be due today at 11 o'clock. Now the old homework, the homework that I assigned before I switched it to Central Time, it's been a pain in the rear to change the due time. So just be aware that it's due at 10:59. I have managed to get chapter 14s at midnight. So you're going to have to pay attention to whatever the time setting is, because it has been a little bizarre in terms of that part. The quiz for chapter 13 was remaining chapter 13. Let's see, I thought I changed these yesterday. So I have chapter 13, sections 1 through 4 is due tomorrow at 11. Remaining chapter 13 is due tomorrow at 11. And then the quiz is due, I'm going to go ahead and change that. Let's adjust, edit assignment settings, because that's just not fair. That's not what I want. Close. It's not settings I want to change the date. That's okay. That's all right. Save and continue. That's the quiz. Yeah. Slightly to the left. That. A little bit more. Okay.
You should probably turn it.
Okay. All right. Can't see what? Video? If you can't see the video, I'm broadcasting video, so are you accepted video? You're seeing the video, video, right, Brandon? Come back, go out and come back in. Okay, continue, and that we want to make it do, and do it that way. Save and finish. And what the heck, I'll be nice.
Do you think that you'll move the midterm?
I will not move, I was going to talk about that. I'm not going to move the midterm, just all the topics covered on the midterm will be shifted. I haven't written the test, so I can put what material so the midterm is still going to be on the 31st. It's just what material will be on the midterm.
So it'll probably just be 12 and 13. We may not do it.
No, you'll get 14 too, because 14 is going to, I can probably do 14 today, chapter 14 today. The theory part of chapter 14 I can get done today.
Okay.
And the same with chapter 13. The theory part of chapter 13 isn't that complicated. It's just doing the example problems. So the theory part is, you guys already have the theory. It's just a little bit different in terms of the vector mechanics on it. Okay, I'm going to go back. Okay, just cancel here. All assignments. Okay, so chapter 13, those are all there. And I want to fix this one. It was a little entertaining. Almost got my bathroom ready, so, okay. I don't have a basement. My pasture did get flooded. And for right now, I'm going to leave chapter 14 where it is. So that should actually, so things, even though they've been out there for a while, you guys now have chapter 28, or chapter 13 is all due on the 28th, which is Tuesday. Remember, on Monday, we won't meet at all because it's Memorial Day, and that was our scheduled day off. And then we got chapter 14 there. So, I'm going to do the theory stuff and get us to where we need to be. See, I actually went and bought pens too. I went and bought pens so that I had pens. So now I've got to go from here. Now we'll look from the page. Now how's the page look to you guys? The screen look to you guys? Okay, you got that? All right. So we'll still have the test on the 31st. I'm debating about how to do the test because I've got people in all kinds of different spots. What I'm leaning towards right now is to go ahead and do the test inside Mastering Engineering, but setting a time limit. So it's time. Everything else I don't set time limits for. So I would set it for a time limit for 3.5 hours, which means it's open book, open note, open whatever. All right. And we'll start it that it's available at noon on the 31st, and I'll give you 24 hours in which to do it, from noon on the 31st to noon on the 1st. So you guys can pick what time, whether, for those of you that are doing internships and have an internship, you would have plenty of time to do it in the evening. For those of you at different job sites, that's kind of what I'm leaning towards for the midterm. And then for the final, I want it proctored. I want an in-person proctored final, and that gives you guys that are doing internships a chance to figure out how to get that accomplished. Yeah.
So you said we have like a 3.5 hour time frame?
Yeah.
So let's say if we're working on the problem or working on the test and something happens where it interrupts us taking the test, can we pause it and then come back to it later?
I'm not 100% sure. In that case, you'll have to email me and I'll have to make arrangements.
Okay.
Because I think with these, once you're in it, you're in the test. And hopefully we won't have any of those kind of issues, you know, especially if you're and that would be a case that you'd want to be hardwired versus trying to do it through Wi-Fi. But I'm thinking that's kind of how I'm leaning towards doing the midterm, because that gives us plenty of time to set that final and give us a couple of ways of leeway in order to do that final and be able to work. So give me some feedback if that's going to be acceptable to everybody. And I'm looking at a 3.5 hour time frame to do the test. It will be through mastering, so you guys, you know, everybody's got that aspect to it, but you know, it'll be open notes, open book, all that piece. But it will be time constrained, and it has to be started in that 24-hour window.
Can you make it easy, please?
Well, you know, it's all.
It's open book, open no. I mean, that's not easy.
All right. Yeah. I think it will be one attempt for the test. Yeah. But the other thing I will do, and I will do the same thing I've done before, is if you photograph your notes and you photograph your problems that you work, I can give you some partial credit. So, yeah, it's not going to be an all or nothing. It's just going to be a case of, but you'll have to submit your notes so that I've got that from a partial credit point of view. Right, but I lean towards partial credit, so okay. So let's get some going through here. All right, so chapter 13, we've done so far what we've done is kinematics, and you guys do have my notes. I've posted them. And so we've done that kinematics portion. Some key things to think about is when we did things like v final squared is equal to v naught squared plus 2a change in our position. This was a constant acceleration. Okay, that was a constant acceleration. And what we did then is we made it more complex in that we started saying that doesn't have to be constant. We actually worked through and worked some problems where that didn't have to be constant. So what were happening in chapter 13, just like we did in our engineering physics, is we started looking at Newton's laws. And things that we did in Newton's laws were fairly straightforward. I mean, we had that, for every action there's an equal but opposite reaction. For every, an object in motion remains in motion unless acted upon by another force. And then we got our classic representation of the sum of the forces are equal to mass times acceleration. Now, for the most part, in engineering physics, we dealt with, okay, we've got this here, but most of the time that acceleration was just like this one. It was a constant acceleration. We didn't deal with something that was a variable, okay? We didn't deal with a variable at all. But we also talked about that this referred back to that mass was an inertial quantity. That mass and inertia were related. And if we think about it, what it is that this is a quantitative measure of the resistance of the particle, because we're dealing with particle, and this could be the particle, could be a rigid body, could be anything. And so when we start doing rigid bodies, if the particle and the rigid body kind of are interchangeable right there, to a change in its velocity. So even though we talked about that, you know, from a qualitative standpoint, what mass was, now we're really figuring it out as a more substantial piece, and we're putting some more things about it. And this essentially is inertia. Okay, that essentially is inertia. We also always talked about that mass, okay, weight is a force. Weight is a force and mass is not weight. Now, we did show, and we actually talked about it, that if I do this version, which is the most generalized version, and what we said, that if I'm dealing with Earth here, that this little distance, if I'm dropping a ball on top of the Earth, to the Earth, that this little delta R is much, 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 much smaller than the radius of the Earth, that I could disregard that distance, and that my force associated with that, we could do this as the mass of the Earth, the radius of the Earth squared, and this would be the mass of the object, right? And since if that's much, 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 much bigger than this, this ended up being G, which we now know is 9.81 meters per second squared, or it's 32.2 feet per second squared. Okay. So this, and remember big G, just so you have it in your notes, they do 66.73. And I love our books, our notation. And this is meters squared, kilograms squared, second squared. And that's just a fundamental constant. So this is the most general form. We end up getting weight, and so we can look at that weight in the y direction or in the z direction, depending on how we ended up doing it. So what we have to worry about is something that we call the inertial reference frame. And this is the acceleration of the particle measured with respect to a reference frame that is either fixed or translates with a constant velocity. So we got, and this is when we apply, and this is for when we apply the sum of the forces is equal to mass times acceleration, where both force and acceleration are vector quantities. So the way to think about this, oops, I'll put a nice E on there so that the notes look nice and better in the video. Get a nice reference frame. So if I've got a boxcar on a train, and I have a pendulum hanging down on this boxcar.
Do you know what problem this is?
This isn't a problem.
No.
This isn't a problem. So I got a boxcar with my pendulum hanging on there. If I'm traveling at a constant velocity, the pendulum is going to hang down. Think about from the rear view mirror. If I'm traveling at a constant velocity, what's happening to my beam? It's not moving, it's just hanging there. Fuzzy dice, all there. Okay? So I can apply F equal ma to that particular situation and life is okay. Now we do know that if I'm going to get a deflection. And this was one of the problems that I do in my engineering physics class, is we do that deflection with the angle to show that, hey, I can be going up or down an inclined plane, and I get a piece that's associated with that. So this is what this is talking about, is as long as I'm traveling at a constant velocity, we know what we can do. If I'm traveling at a constant velocity in here, I can shoot paper airplanes to my buddy, right? I can toss a ball back and forth, and it doesn't matter that my boxcar is moving. As long as it's at a constant velocity, everything's going to work out nicely, and it doesn't matter if it's moving. So it's going to be just the same as if I were outside of my boxcar on, quote, stationary ground. So for it. Yeah.
So the other day you were talking about like relative position and stuff like that.
Mm-hmm.
Like you said how like we're sitting here in this room and it feels like everything is standing still, but we know that the Earth is turning at God knows how fast.
Right.
Is that kind of how that is? Is that like an identical example?
Yeah, that's an identical example.
Okay.
Because I can be in that going back to that same type of an example. Let's say I'm in the car or the rail car and it's traveling at 5 meters per second, and I'm traveling in the car at 2 meters per second. If I'm doing all my calculations inside the rail car, I'm traveling at 2 meters per second. And how things are going to be affected is at the 2 meters affected. But if I'm looking at it from a relative motion from an observer up here, it looks like I'm moving at 7 meters per second. Because I'm taking into account both the motion of the rail car and the motion of the person in the rail car.
If the Earth was accelerating, then
We'd have some issues. Okay, so now what's going to happen is we're going to extend this. We're going to extend our equation of motion to a system of particles. All right, so just like what we did in engineering physics, I've got this blob, all right? And this blob can be made up of a bunch of individual particles, and we're going to look at the ith particle, okay? We're going to look at the ith particle. And this system of particles, there's no restriction in the way that the particles are connected. So this system can be a solid, it can be a liquid, or it can be a gas. Okay, we're going to play with it being a solid. This is where fluid dynamics comes in. Now you know why classical dynamics or classical mechanics starts first. Because if I'm looking at with a solid particle, we know there's a good relationship between each one of these other particles, right? They're connected in some form or fashion, and I'm not necessarily going to have something weird happening. But think about what just happened to us here recently. Okay, so let's take our little tornado here, right? I got my tornado. Now, they were tracking the tornadoes in terms of the motion because I could actually take this entity as one body and look at its velocity as it's moving along. That doesn't take into account what was happening in the fluid along that part of it. But what I could do is take how did this thing move with relationship to the ground? I had a lot of things happening, but I could do this part, and this is kind of the part that we're looking at in terms of a particle, because I'm taking that tornado as a particle, and the storm was moving. So depending on where I'm at or what piece of information I'm looking at, I'm going to break up my system into how I can motion it, okay? So what we are looking at when we do this system here, we're looking at internal forces. And that is the resultant, and this is going to be, internal forces are going to be Fi, is the resultant of all the forces that are exerted on the ith particle as a result of all the other particles. Okay, so I'm looking at how that one's reacting, how this one is reacting, how that one's reacting, how that one's reacting, all the other particles. This is going to be my internal force. That's where I'm worried about what's going on inside my cyclone. Okay, I'm looking at all the other forces that are going on in terms of my cyclone. But what we're going to be more concentrating on is the external. And that's our capital IF. And this represents the effect of all the forces between the ith particle and a body or particle not included in the system. Okay, so the external stuff is, so I've got my crate, and I've got some ith particle in my crate, and I'm worried about the force that's being applied outside of the system. Okay, so I can think of this as a box of puppies in here, or cats, we do Schrodinger's cats, and the interactions that are happening inside the box don't really care about. I'm worried about what's pushing on the crate. Okay, that's what I'm worried about, is what's pushing on the crate. So the total forces that we have, right, the total forces that we have is I end up with the forces that are like this. These are the external, plus my forces that are the internal, is ultimately going to end up being the sum of all the little mass i's, all the little acceleration i's. But if I look at this system a little differently, okay, but look at this system a little differently. There's my little ith box. There's an R, there's an R, there's an R, there's an R. We end up with the mass times acceleration, where this relates to my center of gravity, and MRG is going to be the sum of my little MIRI's out there. And it's a long way to get to the fact that I now look at my sum of my forces as equal to the mass times the acceleration of the center of gravity. Again, my box is filled with a bunch of puppies. I'm not worried what's going on with the puppies inside the box. Other than if all my puppies are laying down on the bottom, it's going to change where my center of gravity is. But I can look at this system and what's happening externally to this system just by following what's happening in the motion on the center of gravity. And conceptually, we had talked about that earlier on. And conceptually, we've got that, it's something that we know. And so my acceleration vector is, at least in my x, y, and z coordinate system, is going to be the acceleration in the I direction, plus the acceleration in the y direction, plus the acceleration in the z direction. And so I can look at my sum of my forces in the x direction, sum of my forces in the y direction, and the sum of my forces in the z direction. So I can look at it in terms of those x, y, and z coordinate systems. Now, I'm going to skip ahead because we'll come back and work some problems, but I want to cover the theory so that we can get through chapters 13 and 14 in a timely manner, since we lost Monday and Tuesday. So we can move from our XYZ coordinate system to our radial coordinate system. And I recall, if I'm looking at that, I can look at my acceleration in the tangential direction and the acceleration in the normal direction. And if I follow along a path, I look at my curvature, here's my force in the normal direction, here's my force in the tangential direction, and then I'm going to have some other in my z direction, and our book chooses to call it B. Yeah, that's why they choose to call it B. But we choose to call it B. And what happens is my sum of my forces are going to look at this. I'm going to have the sum of the forces in the unit vector that's tangential. Here, that's the normal, plus the sum of the forces in the unit vector that's in this there. And that's all going to equal the mass times my acceleration that's in the tangential plus my mass accelerations in the normal direction. And so I end up with the sum of the forces ut is going to equal mass times my tangential. Sum of the forces un is going to equal mass there, and then this one goes away, makes life nice, but I end up with 0. And this ends up, all right, we get AT is equal to our dV dt, and AN is equal to V squared over R, where this row where this is the radius of curvature. And we end up with this one giving us our centripetal acceleration that we've seen before. Yeah. This one? This one? If I look at this one is, so if I'm on a curve, right? This one is towards the radius of curvature. This is Fn. Okay, where that's my unit vector in the normal direction. Then I have my unit vector, or my f of t, where this is the unit vector in the tangential direction. And in my coordinate system, if I've got another vector that's 90 degrees to that one, and I have another vector that's 90 degrees to that one, and that's my unit vector in that direction. Yeah.
What are your values on those arrows right there? It's hard to see what they are. It's like f of n, f of b, and f of t, or c.
F of t.
F of n, f of b, and f of t.
Right. This is normal, tangential, and that's perpendicular to the normal and tangential.
Thank you.
All right. That's all the theory in chapter 13. That's it. It's F equal ma. Right? Lots of different problems, lots of different issues, lots of different things that you have to look at, but that's all the theory.
So all it boils down to is just setting one side equal to another thing?
Pretty much. The big part is when you're working the problems is not making them too complicated, and the trick to all of this stuff is like this one. All right? If I'm tracking the path of the tornado, it's pretty straightforward. But we tend to get lost in the complexity of what's going on in the tornado. Right? Yeah, we think, you know, but all I want to know is it going to hit me if it's traveling at 45 miles an hour and it's coming from Perry? How soon is it going to hit Tonkawa if it stays on the ground? Do I care about how fast it's spinning around? No. I care how, you know, which is it coming straight for me? Right? That's what we care about. The key is what is the question that's being asked. That's the key. The key is what question is being asked. And it's the same thing like my box car. Okay? My box car is what's my system? What's the system that I'm looking at? And I'm looking at how that system is being evaluated. What I always told you the joke about the physicist. How does a physicist define a cow? It's a sphere with the milk evenly distributed throughout. Because if I'm worried about how my cow is going to travel on the rail car, I don't care that the cow's got 4 legs. I'm looking at the cow as where it's the center of mass of the cow. And how's that center of mass moving? Okay, so the trick is setting up your system. That's where the tricks lie. That's where the problems lie. So we're going to start chapter 14. We're going to do a little bit of theory in chapter 14, and we're going to cover a lot of the theory really quickly, because that gets us started with looking at, okay, I got a lot of interesting theory here, but it kind of all comes down to one particular part. So chapter 14, tomorrow, and we'll even start some problems today, because I got time to start some problems today. But chapter 14 is, okay, we've got Newton's laws here, but what's the next step? Energy. Work. Right? So the next step is energy and work. And we liked that because I got rid of all the vector stuff. If I could go to energy and work, I didn't have to keep track of all my vectors. I didn't have to keep track of what was going on with my vectors so much. I didn't have to keep track of am I up or down, if I added them correctly. I didn't have to keep track of that part. If I could do this, that we get. So this is the fun part, okay? So our book is going to define work a little differently. We're going to find it from a force. So a force will do work on a particle only when the particle undergoes a displacement in the direction of the force. Okay? So we're only going to when we're moving along the displacement of the force. So if I have a box and I have a force being applied and my box goes this way, we know that this is the only component of the force that's doing any work. This component of the force is wasted. Okay, that component of the force is wasted. We also have our energy definition, and energy is the capacity to do work. But this whole piece right here gives us this. Now, our book is going to use U for work. And we're defining it as that dot product there. So I can actually do my path, and I have something that's traveling dr, and I have a force that's being applied. The only part of the force that's going to come into play is the force that's along the path. And I get the age-old. So if I do my path, let's do this. Change this a little bit. So I have my path that I'm following. Here's point 1. Here's point 2. So U from point 1 to 2. If I'm going here, right? This is my change in position. And I have my force that's being applied, and here's my angle. This is the magnitude of the force, cosine of that angle, S2 minus S1. And that was our work that we've seen before. But this forces were steady. I'm applying 5 newtons of force. I'm applying 10 newtons of force. Right? My forces were steady. We talked about it. We didn't do a whole lot about it. This is S and this is F, cosine of the angle, right? I could have something that looks like this. And if I know this function, we can figure out the area under the curve, right? Because this is my small change in S or ds. And work is the area under the curve. And we use this to do, if I have a spring, right? We know that the force was equal to minus kx, right? Where x was my compression or extension of the spring. This was my spring constant. And we plotted force versus x, right? We plotted that. We got a nice straight line. And we said that the work done by the spring was equal to 1/2 kx squared, which also was the potential energy of the spring. And for grins and giggles, our book is going to use S or V, a capital V for potential energy.
That's just malicious.
It's malicious, and and it even gets worse. They're going to use T for kinetic energy. All right, so U, now granted, work is energy, so I'm okay with the U. But to kind of keep things straight, they're using T and S, and you're just going to have to remember that this T is not tension. Okay? It's a little bit funky. But we did this before to get that spot.
Can we just use our own units?
Well, one of the things that I end up doing, so we'll go back. So basically, if I'm doing the area under the curve, I can rewrite this and remember, I'm doing a dot product, right? So this is the more general form. If the force was a constant, no, that's not d theta, sorry, that's habit. This should be ds. No, it's just DS.
Okay.
It's just because I'm integrating from S1 to S2, I'm integrating over small increments of S. I got into habit because I wrote a theta there, and I wrote a d theta, and it shouldn't have been a d theta. It's a ds.
Would the first part be for radiuses? The
No,
FDS?
this is generalized. This is totally this is just a displacement. It's totally generalized. But if my force is a constant, this gives us our general form that we know and love and have worked with before. Because my force, my cosine, now I'm doing S1 to S2 ds, right? Now I'm doing F cosine theta S2 minus S1, which is the one we've seen before and the one we've worked with before. Right? Little easier to deal with. Okay, but now if we do a dr that looks like this, and I've got a force and I do my force dot dr, that's my more generalized form, right? There's my more generalized form, because this is my force vector, this is my dr vector, I can do that. So let's just simplify something, right? Let's look at weight. So if my force happens to be weight, that's going to be the weight, negative weight in the k direction. And I'm going to deal with a dr. And I'm going to look at the work done. And recall I dot I equals 1 equals J dot J is equal to K dot K. And I dot J is equal to I dot K, which is equal to J dot K equals 0. So then my U12 becomes my integral of minus W, and I did this in terms of Z. Looks pretty familiar. So we end up, and we can do it this way. If I do F dot ds, oh no, let's start different. If I start with F is equal to mass times acceleration, and this is equal to v dv ds, and then we get F ds is equal to mv dv, And we do the integral f ds is equal to the integral mv dv. And we end up with work. And this ends up being 1/2 mv2 squared minus 1/2 mv1 squared. This is the change in kinetic energy. So we end up with our work, energy, theorems. Just coming at it a little differently.
Do the same thing, but differently.
We're just coming at it a little differently. The big difference is when we did our work energy theorems, we were dealing with a force that was relatively constant. We weren't dealing with a function. So what's going to happen to us is the tools that we have to use in order to solve the problem are going to get more complicated. We're going to do the integration. We're going to do, and we're ultimately going to get this one. We're going to get this function, okay? We're going to do the dot product, which is going to lean to our d dx plus d dy plus d dz. Okay? We're going to start getting that particular gradient function to come into play. A couple other things from a theory-wise for chapter 14. Power now, we just can't do work divided by time. It's going to be the differential of work with respect to time. And this is going to look like du dt. And that's going to end up being dt dr. And then we can also show that power is now, or that's a velocity vector. Okay, little differently than what we're used to seeing it. But this now makes a heck of a lot more sense when you're talking about drag racers.
They use that equation in weightlifting.
Yeah, same thing. I mean, it's a heck of a lot more sense now than just running up and down the stairs. You know, well, how's that power? Because we think of power in terms of weightlifting, we think of power in terms of drag racing, we think of power in terms of a variety of other things. So to see it in this form versus seeing it as the change in work with respect to the change in time, it's not as intuitively comforting. Whereas this one is more intuitively comforting.
So like, if let's say you have a football player
Mm-hmm.
and you like somehow are able to double his velocity, so
Mhm.
instead of running at 25 miles an hour, he can run at 50 miles an hour. He'll have twice as much power.
Yep.
Because
Yep.
mass times acceleration.
Mm-hmm. Yeah. So you end up with this is a lot more. This one makes more mental sense to how we view our world than that one does. And then efficiency, which we're going to use a script E, which we get the power output divided by the power input. And for machines, always less than 1.
Would it be a perpetual motion machine if it was equal to 1? Yeah, perpetual motion can't be.
Yeah. This about it there, it says everything's going into work, and that if it's equal to 1, I'd be in violation of the second law of thermodynamics. All right. So So that gets us most of the theory in chapter 14. So the next part is crunching the problems. And the tricky part isn't the theory. The theory we're comfortable with. The tricky part is setting up the problems. So we're given a block. So going back to F equal MA, we got a block. Okay, we're going to apply a force, except my force is going to be applied at 8t squared. There's my first change in how I normally dealt with a problem. Okay. The initial velocity was 4 feet per second. And the box has a weight of 10 pounds. The other thing that we start doing in dynamics is that we no longer disregard friction. And we are given that there's a kinetic energy, or the friction, kinetic friction is 0.2. We want to know the velocity after the block has traveled 30 feet. Okay, if we were doing this with our traditional problem, we still know that F is equal to mass times acceleration. Okay, traditionally, I don't want to do this. Traditionally, we would have just gone in and solved for our acceleration. So let's do that. I can do that. My change in velocity is going to equal my acceleration times time. I'm doing it from 4 feet per second to a final velocity. And I'm going from just 0 to 18. Okay, so I'm going to do, so I get V final minus 4 feet per second is equal to 8t squared dt. Is that how I want to do this? Oh, I know what I did. I've played with this a couple of different ways in my notes, and so I'm having a lot of fun. All right, we'll come back to that. All right, sum of my forces is the force being applied is 8t squared minus my force due to friction. Okay? Minus my force due to friction. 8t squared minus, and this is my 0.2 times my 10 pounds, because friction is fun. This is 8t squared minus 2. That's the sum of my forces. acceleration. Okay. Mass is going to be my 10 pounds divided by my 32.2. So I'm going to get 8t squared divided by 10, 32.2 minus 2 divided by 10, 32.2. Now I'm going to come in 4 feet per second to my final velocity, dv, is equal to that acceleration times time. So now I'm going to do my 32.2 divided by 10, 8t minus 2 dt is going to equal 32.2 divided by 10, 8t cubed divided by 3 minus 2t, 0 to t. And this gives me v minus 4. V is equal to 8,587 t cubed minus 6.44 t plus 4. Then we got to do the ds is equal to v dt. That comes in there for v. Ultimately, I get s is equal to 2.15 t to the 4th minus 6.44 divided by 2 t squared plus 4t. You can play with this and do a change in s is equal to v naught t plus 1/2. Nope, can't do that one. Plug in this, we don't know t. So in this one, plug this at 30, no. We plug in our 30 feet here and then solve numerically. And when you do that, you get t is equal to 2.0089. Plug that back up into there, and then you get v is equal to 60.7 feet per second. Yeah. That came from the problem. We wanted to know the velocity after the block has traveled 30 feet. Do it numerically. Plug in numbers until it works. Put it in Excel. There's a couple of numerical methods that you can utilize. They're not pretty. None of them are pretty at that point. Okay, let's do one that's a little more fun. We're given a curve and this is a velocity versus time curve. Our car is a 1.5 megagram car. It's traveling with a force, so we're given the force, and it's a nice constant force of 4.5 kilonewtons. And the velocity, this is going to be, the velocity is equal to minus 0.05 t squared plus 3t. And we want to know the air resistance. So essentially what we have is our car we've got our air resistance R. We have our force going this direction. And we got a normal force coming down here, which is our weight, which is going to be our 1.5 10 to the 6. And we're in newtons, so we'll do the 9.81 thing. So you've got that part in there. But my sum of my forces are going to be the force that's applied minus the resistance is going to equal mass times my acceleration.
Wouldn't that weight give you grams per gram?
It's megagrams.
Yeah, that's the 10 to the 6, but when you still need a 10 to the 3rd, you got
So it's in
kilos.
newtons.
Yeah. So it's going to be 10 to the 9th.
Yeah.
No, it's 10 to the 3rd kilograms. Going the other way. It's 10 to the 6th grams, but if I want in kilograms, it's 10 to the 3rd.
Alright. That's too much thinking for me.
A is equal to dv dt. So this is going to be d dt of my minus 0.05 t squared plus 3t, which gives me a minus 0.05 times 2t plus 3, which gives me a minus 0.01 t plus 3. Applied force minus R because that just needs to stay in mass, so that's all right. This is 4,500. Solving for R. If you do it as negative R, you get negative 150t plus 4,500 minus 4,500. So that ends up, you get R is equal to 150t. Okay, one we've seen before. For those of you who haven't had me in engineering physics, this is known as the penguin problem. The penguin problem. So this time what we're going to do is we're going to have a truck. And on this truck I got a flatbed here with a box. The box has a mass of 200 kilograms. It's a big box. Coefficient of kinetic friction is this one's static friction. Coefficient of static friction is 0.3. And we want to determine the shortest distance the truck shortest distance for the truck, we'll put in there, for the truck to reach 60 kilometers per hour without the box sliding off. So first thing I'm going to do while I'm thinking about how to kilometers per hour to meters per second, you know, it's a good stalling technique, and I'm probably going to need it anyway. Meters per second. Probably going to need 100 kilograms, 9.1962 newtons. Force due to friction, and so if my force is greater than 588.6 Newton, I'm going to slip.
Wait, hold on. Why do you call it the penguin problem if there's no penguins involved, just a box?
But remember the penguin problem with the penguin on the sled? In General Physics 1 or Engineering Physics 1?
I think so, like, kind of.
If you went back to your notes, you'd go look at the penguin problem. We did exactly.
I remember doing something like this, like trying to figure out, like, okay, if the force is this much, then it'll slide off. Like, I remember doing something like that.
That's the
but,
penguin problem.
Something involving a penguin, I don't quite remember.
Yeah, that was my penguin problem. We did the penguin on the sled, and if I pulled the sled too fast, my penguin was going to fall off the sled. Yeah, this was the penguin problem. It's the same thing, except we're using a truck and a crate. It's the same problem. You know, it's something that slip off of the object.
Now, the problem says determine the shortest distance.
Right.
Like,
But if that's but that's the thing. If now the thing is, if I want to determine the shortest distance, this means my force. If I'm going to go 588.6, that's my mass times my acceleration, right?
yeah.
So I got my 588, and that's 200. That's going to be my acceleration. Okay, so if the acceleration exceeds that, which happens to be 2.943 meters per second squared, if my acceleration exceeds that, it's going to fall off. It's going to slip. Right? So now I do velocity divided by acceleration, gives me time.
But what if it said like the longest distance?
Oh, the longest, that's easy. You can go, you can drive very, very slow and
That's what I was wondering. I was like,
yeah, no, that one's easy. The shortest distance is going to be that, and that's 6.67 divided by 2.943, and that's going to end up being 5.66 seconds. You do it shorter than that, crate's off.
So, like, you could hypothetically, because I remember one time I went and I got, my mom sent me to the store and I got a birthday cake and I meant to put it inside of the cabin of the truck with me, but I put it on the toolbox of my truck, and I got my truck and I forgot, and then whenever I got home, my cake was still on there. So it's like, but if I was going too fast, it would have fallen off.
It would have fallen off.
Okay. That makes sense. And the heavier something is, the less likely it is to slide off.
the more.
No, it has more. It has more of that. A lot more of that. As long as depending, that's why if I've got gription, got the bed that's got a lot of gription, I could have something very light. If I have a high coefficient of friction, I'm less likely to have something fall off.
So it's more.
It's a combination of things. It's more weight, and it's because it's related to that normal force.
But it's better to have the higher coefficient of friction than it is the mass.
It depends on what you're doing. It depends on what you're doing. All right, let's do some that are in. Okay, well, this is our mean merry-go-round here. Okay, our merry-go-round. So this has got a merry-go-round. This has a radius of 1.5 meters. The mass of 25 kilograms. Coefficient of static friction is 0.3. Merry-go-round slowly enough that our tangential acceleration can be neglected. Okay, so we're going to go slow enough that we can be neglected. We want to determine the speed at which she begins to slip. Told you.
I remember doing something like this.
Yeah.
It was like an evil carny, just playing with the levers.
You got it. So the normal force, okay, is going to be mass times my normal acceleration, which is mass times v squared. In this case, I can use the radius of the merry-go-round. Okay, so now I've got mv squared divided by 1.5. If I look at my normal force and my force due to friction, 25, 9.81. So now I got 73.5 is equal to my mass, which is 25, 1.5 v squared. V squared is equal to 73.5, 1.5 divided by 25. V is equal to 2.1 meters per second.
So that's what tangential velocity is.
Well, in this case, this is the velocity, yeah, or the linear velocity. So I've got a section of a roller coaster. We've got a car on the roller coaster traveling along the track, and at the time, the track is defined by, so our track is going to be defined by R is equal to 3/4 Z. Theta is equal to minus 1.5 Z. And we're given that theta dot is equal to 1 radian per second. R and Z are in meters. Theta is in radians. And we want to determine the force exerted on the car by the track and this is going to be R, theta, Z, or coordinate systems, when Z is equal to 6. And the mass of the car with passengers is equal to 200 kilograms. So basically what we've got here is a system that looks like this. We've got our little car. This is Z. We have mg is equal to 200 kilograms, 9.81, and this is equal to 1962. And this is going to be in the Z direction. So the track's got to come up in the Z direction, opposite that. So now, some things to stall by, right? Okay? Stall while you're thinking through the problem, going, all right, so we're going to do this, because I'm probably going to need them while I'm stalling to think through the problem. Oh, no, wait, no. There we go. We'll stay more general to start off with. But if this is 1, because that was given to us in the problem, that's got to be 0.
Just because it's a constant.
Well, yeah, because we know what that is, right?
Yeah.
Right? And then we get, that also tells us that Z double dot is equal to 0. Which means that's equal to 0.
Wouldn't it just be the normal force? Because that's the only force that the track would exert on the
Nope.
car.
I'm holding on, unless I'm flying off the track. Okay, at Z is equal to 6, R is equal to 4.5. And I end up also, I have it in my notes and it's just not coming to me. What am I doing per second? Oh, that's it. Just right here. Minus 1.5 Z dot is equal to 1. Z dot becomes 1 divided by 1.5. Negative 1.5, it's negative 0.667. So now, so at Z is equal to 6, R is equal to 4.5, R dot is equal to 0.75 times a negative 0.667, which ends up being a negative 0.50. R double dot is equal to 0. A tangential is equal to R double dot minus R theta dot squared, which is now going to be 0 minus 4.51 squared, which is equal to negative 4.5. Normal is going to be r theta double dot plus 2r theta dot. So I get 0 plus 2, negative 0.51 gives me a negative 1 meter per second. FAT becomes 200 negative 4.5 equals 9 minus 900 newtons. FAN is 200 minus 1 is negative 200 newtons. I have a couple of others in my notes, but hopefully you guys opened my notes before.
Yeah, I printed them off for class.
So I have a couple of other ones in there, and I haven't had a chance to. Well, that's what we will do tomorrow. Back up.
Wouldn't they be going in a negative direction? Wouldn't he be going back down the loop instead of forward?
Oh, I don't have my loop drawn correctly. This is what the track is exerting on the car. So the car's going one direction, the track's reversing towards it. Equal action, but every opposite reaction.